everybody. I'm Samantha Siow. I'm a senior front-end engineer on the front-end foundations team at Slack. And I'm going to talk about how we made our new rewrite of the desktop app 33% faster at boot time. For anyone who doesn't know what Slack is, it's an application that enables workplace communication and collaboration. The Cascadia organizers actually set one up for us, which is really neat. So let's get into it. So on the left, we have our legacy app, and on the right, we have our new and improved app, which I'm going to refer to as the modern app, which we launched in July. As you can see, we have huge differences in the UI. It's just completely redesigned, specifically with this plus button here and the paperclip button. That's how you tell the difference. But most of the differences are actually behind the scenes because it was a complete movement in our architecture and technologies that we use. So let's step back in time to January 2014 when we launched our Slack open beta. So we were building for around 250,000 daily active users at the time. We had 4 front-end engineers working hard to get this out to the general public. So this is 2014, so we were adopting technologies that were widely used at the time. So let's go into sort of the architecture and our tool set. So we use handlebars and Smarty templates for our UI. We use jQuery to manually update the DOM according to changes in the data model. I don't know if any of you remember jQuery. Those were the days. We had multiple processes per workspace, and workspaces are what you're signed into on your app. And so this meant that CPU and memory usage were directly increased and correlated to how many workspaces you were signed into. And then lastly, we had an eager data loading model, which I'm going to talk about a little bit more later. So jQuery, handlebars, Smarty, these were all very popular technologies back in 2012 when this app that I am working for was just started. And in 2017, we started supporting React. And that's when we started migrating some of our existing features over. But a majority of our client was still using these older technologies. Is it? OK. And so jumping forward to January 2019, and it's 5 years later, and we have 10 million daily active users and just over 120 front-end engineers actively working on our client. That's 30 times what we were in 2014. So with more people using Slack, more messages, more channels, more larger teams on our platform, and more engineers adding features, in order to better support our customers, which is all of you, we wanted to make our app more performant. And also, in order to support our engineers, we needed to make product development more easy and reliable. So let's talk about the modern architecture. So there are 3 rules we wanted to enforce when we first started building the app. And this was, number 1, first, that all UI components were built in React. So this would mean that the building UI would be a lot less prone to errors and actually going in and selecting the components you wanted to update. And then also that the UI updates would be mostly automatic. There'd also be a single process per workspace. So this would give us huge gains from a performance perspective, because now you're no longer tied, your CPU and memory usage is no longer tied to how many workspaces you're signed into, and you would use a lot less CPU and memory. So lastly, a lazily loaded and incomplete data model. Oh, why is it doing that? But we'll talk more about this later. So side by side, we can see the difference in boot time with legacy on the left and modern on the right. And the modern app loads 33% faster, which is crazy. It's awesome. So in this presentation, I'm going to cover 3 optimizations we made that contributed to this 33% faster boot time, some challenges, some learnings we made, and maybe this will help you also consider applying this to your apps and getting this faster boot as well. So here are the 3 optimizations. We're going to go through them in a bit more detail, but I want to first start by saying it's very important to profile and find the bottlenecks and see where there's room for improvement, because that's where we started as well. So we'll start by saying load less code up front. So what does this mean? It's pretty simple, but for our app, it got a little bit more complex. So we'll look at this profile for the legacy app boot process. And over here is where we initially downloaded all the JavaScript required to run our app. And we have a lot of JavaScript. Since our app is like the single-page, long-lived app, we had to download all of this up front in order to run everything. And also, we had a fairly simple build process at the time where everything, all our JavaScript was kind of smushed together into one file and then downloaded at once. And this took around 700 milliseconds to download for this app, for our app. And so if we include the other assets we have to download, which is loading images, CSS, and our templates. As I mentioned before, we did a bunch of server-side rendering, which meant that we needed to download these like Smarty and Handlebars templates beforehand so that we could use them in time for our DOM manipulation. This came up to 1,750 milliseconds of downloading time. And as more features were developed, number of assets grew, and so did our boot time because we needed to download more assets. And then, only after all those things were downloaded, were we able to start our initial API calls. And all these API calls are necessary to get the data to boot your app, so we would only be in a usable state when these calls are resolved. So ideally, we'd want to be starting these API calls as early as possible. So to summarize, what were our problems? We have lots of templates. We did a lot of server-side rendering, and because we're this long-lived single-page app, we have a lot of states that our app could be in, and so we had a lot of templates to download. Secondly, we had a lot of code. We write a lot of JavaScript. We have a lot of engineers. We have a lot of features. And because of our simple build process, all of it was downloaded at once, and this took a long time. So this is the modern profile of the modern app. And over here is that same sort of first boot payload. So we have a fast booting framework internally known as Gantry. We just released a blog post about it, and I highly recommend you check it out on our engineering blog. And it creates this small boot payload that handles starting these initial API calls and also downloading the rest of the app in parallel. And this brought our first boot download payload time down to 160 milliseconds, which is a lot smaller than what it was before. And so even better, after we've downloaded that first initial boot payload, you can see here where we start our initial API calls and then also download the rest of the app in parallel, which saves us more time. And we use code splitting and dynamic imports in Webpack to create this the orange bars, these small bundles of JavaScript that can also be downloaded in parallel. So everything's overall a lot more efficient and a lot faster. So time it took to download these assets is 100 milliseconds. And what it was originally, it was 1,750 milliseconds. So this is more than half what it was in our legacy app. But there's even more that we did. So this is the modern app, but with a service worker installed. So as you've probably heard over some earlier talks today, service worker is this new technology that we started using for our new rewrite. And we use the service worker to cache assets. So you can ignore this gray chunk here. We're fetching the cached fonts. But what's more important is that tiny blue dot and all these orange bars. So over here is where we download that boot payload that I mentioned earlier, and it brings the time to download down to 36.9 milliseconds. We also cache the other JavaScript that we use to run the app, which means loading the JavaScript takes even less time than before, especially in low connectivity environments, because we don't need to download it over the network anymore. We can also use the app offline now. So using cached assets, total time to fetch these assets is 1,750 milliseconds in legacy. Was 1,750 milliseconds in legacy, and now it's 550 milliseconds, which is 3 times faster what it was before, and the app is usable offline and in low connectivity environments because we're able to serve from the cache instead of downloading over the network. So to summarize our solutions here, for our problems of having lots of templates and having lots of code to download was client-side rendering, which meant that we don't need to download all these templates beforehand. This tiny boot payload, which will handle downloading the rest of the app and starting the initial API calls in parallel. We use code splitting to bundle our JavaScript assets so they are download very quickly and also can be downloaded in parallel. And then lastly, we use a service worker to cache these assets so we can serve them offline or in low connectivity environments or anytime, and it'll just be a lot faster. So the second optimization we made was decluttering your boot data. So as some of you might know, our app contains a lot of data. And it's data like messages, all the teams you're signed into, members in your teams, user groups, channels, all your unread data. And we have one API call that fetches a majority of this data. This is not something we could run away from because it was required in both legacy and the modern app. And so we needed all this data to boot, and it obviously takes a longer time the more data that it needs to fetch. So in 2014, we had a smaller user base, and it made sense to keep it this way, and it didn't have a big impact on boot time. But in 2019, with more engineers adding features, more users adding data, and larger teams on our platform, having more data to fetch would mean longer boot times. So how could we, as front-end engineers, make this API call that sort of lives on the server side faster? And the answer for us was just fetch less stuff. Fetch less data from this very critical endpoint means less load on the server, it's a faster round-trip time, and it also makes the boot process faster. So easy, just don't need that much stuff. And actually, it's not that easy. How do we do that? So I'm going to talk a little bit about this complete model that I mentioned before. The original Slack client would fetch and store all your data required in your workspace at boot time. So this would be all the members in your workspace, all the channels, and we would keep the data up to date via events over the WebSocket. This meant that this was the complete model, which means that we know everything at all times, and it's always up to date, and there's no fetching required. Eager data loading meant that we were fetching this all upfront at boot time. So over the past few years, we've been moving towards this incomplete data model, where we're only fetching what we really need at boot time. So things like channel membership, user group membership. And then we fetch additional data on demand as necessary according to user action. So this is the lazy loading pattern that I mentioned before. And this decreased network transfer and memory usage because we're only fetching and storing data that we absolutely need and that we know is important to us. So let's go into an example of how that looks on the client. So at boot, we actually don't fetch any of these members that you're seeing here. When this conversation is fetched, we identify that all these IDs need to be fetched, and then we fetch them all on demand and store them locally. So as an example, say you're viewing a message from a user that is mentioning a user that's not in your local model. Because we want to keep the payload slim, this actually only contains an ID in that question mark section. So there's really nothing we can show. So what we'll do here is that we'll check Redux and see, do we have any user that matches this ID in the store? And user doesn't exist, so then we'll fetch it from the server, upsert the response to the store, and then this will make React re-render this to contain more user data, so things like the username preferences, and then you can click through and view their profile and things like that. So it's really neat. So by the time you get here, you'll see that it's fully fleshed out. You have all the data that you need. So our solution, to summarize on that, is to embrace the unknown, specifically moving towards this lazy loaded incomplete data model where you might not necessarily know everything, but that's OK because you can fetch it on demand. This also meant that that big blocking API call would take less time, which meant a faster boot for everybody. So lastly, the last optimization we made was to prioritize our initial API calls. So like that call I mentioned earlier, we have a set of API calls that block boot and that we need to call as early as possible, and that will only be able to resolve, that will only be in a completely usable state when all those calls resolve. So between the legacy and the modern app, we're actually calling nearly the same amount of API calls here, but we can get to a usable state a lot faster on the modern app. And we did this by being more strategic about how and when we call our APIs. So back to the legacy profile. We have these 3 API calls here that actively block boot, meaning that we need these 3 calls to be resolved before we can remove that loading screen that you saw in the previous video. And this first meaningful paint in our terms was that first conversation view, where you can see the last conversation you had open, but you can't necessarily click on other messages in other channels in your sidebar. But the problems here were that these API calls are all made in serial, meaning that this last API call doesn't actually, it doesn't get called until this second one is resolved. And so in between these main API calls, we call a lot of not really that important calls that we could defer till later. So this mix between high priority calls and lower priority calls meant that we weren't focusing on the highest priority things early on. And in the modern app, we wanted a more efficient boot process because we wanted a faster time to this meaningful paint when you could actually view data and not be stuck on a loading screen. And so our problem here was we have this big chunk of API calls. We need them all to be resolved in order for our app to be completely usable. And we have so many API calls. We have a lot of data. What do we do? So there's lots of opportunities for optimizations here. This is the profile for the modern app that we've seen before, but slightly later on. The first thing we did was identify these high priority calls. So what we did here was start from a clean slate. We're building from the ground up here, so we didn't have any API calls at first, and we'd add them in incrementally as we found data was missing that we absolutely couldn't defer till later. So by identifying what we needed really early on, we could make sure that we were only calling high priority things right at the start. And the boot payload I mentioned earlier also meant that we could call these even earlier than usual because we're calling them in parallel with the downloaded JavaScript assets. So once all these high priority calls are done, then we can make the deferred calls. So the high priority calls get us into the state where you can view your last active conversation, and then the deferred API calls sort of fill in the blanks so that your app gets completely usable. We also call these calls in parallel, different from our previous one where things were this long serial serial promise chain. So this meant less idle time, and we were more efficient with our time overall. So our solutions here, to summarize, were prioritize your API calls. For us, this meant calling things like getting that first conversation, getting user data, and that meant that we could get that meaningful paint on the screen as early as possible. Also parallelizing our API calls, meaning that we group them all at the beginning, the high priority ones, and call them all at once so there's less time wasted. And also, if your API calls are blocking boot, you want to call them really early. For us, we only called them after we had, in the legacy app, we'd only start those calls after we had downloaded all our assets. And so by calling them slightly earlier while we're dynamically importing all the other assets that we needed, we could get this first meaningful paint on the screen faster. So to summarize some takeaways, load less code up front. For us, that meant client-side rendering and moving away from having to download all these templates early on in the boot. A small boot payload, this would handle sort of bootstrapping us into place and give us better control over the rest of the boot process. And also, we'd be able to start this asset downloading and data fetching early on. Code splitting meant we could bundle our JavaScript into these small bundles that downloaded really quickly and in parallel as well. And then also using the service worker to cache these assets so you could access our app offline without this big overhead of network transfer at the beginning. Secondly, decluttering our boot data. This is fairly simple, meant that embracing the unknown. So for anyone out there who has a lot of data to fetch, consider fetching data on demand. Maybe think about what you absolutely need at boot time and then fetch other things afterwards. This meant for us lower memory usage because we're not storing a bunch of data you might not necessarily need in your client, and also less server overhead. Lastly, prioritizing initial API calls. So for us, this meant identifying API calls that we needed to get our app into a usable state as soon as possible, and then front-loading those calls. And then also consider parallelizing your calls to save time. We also made sure that we're starting our blocking API calls early on so that they don't block boot and the app from getting into a more usable state. And that's how we made Slack load 33% faster. Internally, our code name for this new app was Sonic, so I thought this would be a good paying homage to that. And here are some references and credits for this talk. These three up here are really interesting and shed a bit more light on some of the things I've talked about. And they're all at our slack.engineering blog on Medium. The rest are just other interesting things. And then this is what I use for my slide themes. And thank you very much. And if you have any questions, you can find me afterwards or on the CascadiaJS Slack team. Thank you.